Okay, so forward pass in a layer block in MATLAB. Before we get to the MATLAB code, let me define it in more general. Forward pass in a layer, in a neural network layer, is simply getting an output given an input and some parameters. Okay, so you give input, you have some parameters, you get the output here. So it is like for this layer, the input is X, the parameters are W matrix or omega if you can call it, and the output is Z. So this function F is the blue one, is the forward pass. What is the backward pass? It is simply getting the partial derivative of the output with respect to the parameters. If you can provide this function analytically, which is, there's a partial derivative here, which is being fed from the succeeding function. In this case, it is delta L over delta Z. So the partial derivative of the loss with respect to the output at this point. So this is the derivative of the loss with respect to this point. And by getting it, if you could just find the derivative of the loss with respect to X and derivative of the loss with respect to the parameters, well, if you can analytically calculate this, that's the backward pass. And if you can give these two functions as some function codes or objects to your framework, whatever framework you're using, Python, PyTorch, TensorFlow, MATLAB, you have a custom layer. And you can add that layer to your layer graph. And in your layer graph, it will be compatible with backpropagation. So how? Let me show you. Actually, we can look at a custom created layer in MATLAB Deep Learning Toolbox. I'm going to show you a custom created loss layer, which calculates the loss. You remember the loss layers? We have output, we have the loss, and we have the targets, training targets. We calculate delta L over delta Y, yes? Yeah, right? So if we could create a layer like this, we can do it. So let's jump to live code here. So this is the function. Sorry, let me just create this. It's not. So it is actually, you use a class definition. The language of MATLAB is very close to all object-oriented languages, especially Java. So there is a parent class which is a neural network layer and regression layer. So there's a parent class already defined in MATLAB. You define this child class under this parent class, and in that class you define some parameters. These are properties. This is optional. You don't have to, but if you need some custom or non-custom variables, you put your variables of that object or class here. Then you have the constructor function having the same name of the class, and you just provide its name here. That's what is compulsory. And you define the forward methods. So the method of a class is the function of that class. When you create the instance of that class, if you know object-oriented programming, you will understand what I'm talking about. If you don't, well, this is how object-oriented programming is. You create an object under a parent object, and you override the methods. So the forward method is called forward loss. You give the layer itself. For this loss layer, you provide the output and the ground truth. So you remember this because we provide the layer itself, the output, and the ground truth. It will calculate the loss for us, right? And it outputs the loss, L. It's called the dice regression layer. So it calculates what is called the dice loss, and you got the loss here. It's the forward pass just provides this loss. So what is the backward pass? Backward pass for this particular loss function will provide dl over dy. What was dl over dy? If you look at this example, it is the output of the backward pass, the derivative of L with respect to y. If you know what you're doing mathematically inside it, you know this function, and you can write this function. And in this example, it calculates dl over dy according to the mathematics of the dice regression, and you feed it out. And when you have this, actually you can add it to your architectures. I've already done it in one of my architectures, and you can create in a layer. This is very important, guys, because we now know that we can create custom layers. And if we can create custom layers in any framework, we can change them in any way we want. Actually, maybe we can write custom quantized layers so that those quantized layers will enable quantization-aware training for us. Actually, we can do it, and we're going to observe quantization-aware training models for different frameworks in these slides. Okay, let me get back to the slides. So yes, how to do it? So if any type of layer can be rewritten for any library, we can write the quantized version of our layers and make it quantization-aware possible. Quantization-aware training possible. Well, major deep learning frameworks have already provided this within just 1 or 2 years' time. PyTorch, TensorFlow, sorry for the typo, it's not X, it's S, or Xilinx Brevitas, they have provided quantization-aware training custom layers. We can add them. And they actually, what they do is, they implement this pseudocode. How to implement this pseudocode, I'm going to get into the details of it in today's slides, don't worry. But currently, MATLAB Deep Learning Toolbox does not have this capability. As we've spoken about this previously, MATLAB is a bit behind compared to other frameworks. So they've published their first deep learning toolbox in 2018. Well, it's 4 or 5 years later compared to their Python rivals like PyTorch or TensorFlow, and they are behind this about this quantization-aware training as well. So if you want to do quantization-aware training using a fully compatible framework, you will need to do it in Python, PyTorch or TensorFlow, in those frameworks. But still, you can create your custom layers, quantization-aware custom layers in MATLAB as well. There's nothing stopping you from doing that. Actually, you can do it in Python as well. I mean, you can do it on any language, but you may have to do it on your own. So how to do it? Guys, do you remember how we created layer graphs by adding layer objects on top of each other in MATLAB? We have covered a lot of examples. Actually, in the previous weeks, we have covered this LXNet quantization of weights. Let me get that live code and just show you an example. You remember the create LXNet architecture function. This created the LXNet architecture for us. Simple, just the image input layer, convolution layer, ReLU layer, cross-channel normalization layer, which is a layer in LXNet which makes normalization of the activations. This is a title from the previous semester's course, so don't worry about it. So all these layers are the layers we have covered in the previous weeks. These are the layers, guys. So these layers we use to construct our network. And actually, to construct it in MATLAB, you just create a layer objects and you put them as if they are concatenated objects, as you can see using the square brackets and this semicolon, and adding these functions. Each of these functions will output a layer object, and you're concatenating these layer objects. This is how you do it in MATLAB. Actually, and frankly, this is how you do it in all frameworks, guys. In different frameworks, it is not different. So now I'm going to show you an example in Python and PyTorch. Well, if you've never seen Python in your lives, this might look a bit alien to you, but don't worry, it is much simpler than it seems. Let's see it. Let's cover it. Since some more advanced frameworks have these quantized versions of layers, we could just observe them, one of them is PyTorch, and understand how we can do it. Okay, let's look at some PyTorch code.